Today we're covering section 4.6 on polynomial inequalities and rational inequalities. Starting off with a quadratic inequality, any quadratic inequality can be written in this form, where we have a quadratic which is greater than some number or zero. And we could have the greater than symbol switched out for any less than, greater than or equal to, or less than or equal to. Quadratic inequality is just one type of polynomial inequality. If I were to switch out this quadratic for any polynomial, a lot of these same rules would apply. And you can see we have some examples at the bottom of the slide. So starting off with x squared minus 4x minus 5 is greater than 0. You're going to see how this is a little bit more complicated than our standard linear inequalities because we have more sign changes to handle. So let's start off by solving x squared minus 4x minus 5 equals 0. And to do this, we're going to factor our function here. And we'll have two x's. And we got to think what multiplies to minus 5 and adds to minus 4. Well, that would be a minus 5 and a plus 1. So then, of course, I said x minus 5 equal to 0 and x plus 1 equal to 0. X equals 5, and we get x equals minus 1. Now we're going to actually plot those onto a number line at minus 1 and 5. And what we're going to look at is what happens from negative infinity all the way up to negative 1 in terms of the sign. Are we positive or negative? Then thinking about negative 1 to 5, and then again from 5 to positive infinity. See, the only place that the sign can change is where we have our zeros, since that's where we might have crossed the axis. To figure out what those signs actually are, we're going to pick some test points. So I would pick maybe negative 2, but anything in the interval from negative infinity to negative 1 would work. Negative 2 is just easy. Let's pick 0, and let's pick 6. We're going to figure out what our function evaluates to at each of those points, see if it's positive or negative, and that'll tell us if the entire interval is positive or negative. So plugging in negative 2, I have negative 2 squared minus 4 times negative 2 minus 5. And here we're looking at 4 plus 8 minus 5. I believe that's 7. Then we have f of 0. And here we have 0 squared minus 4 times 0 minus 5. And that, of course, is negative 5. Then we have f of 6 for our other test point. And we're looking at 6 squared minus 4 times 6 minus 5. And that, again, is 36 minus 24 minus 5. That, again, is 7. So these are all our test points. They're just helping us determine exactly what sign we have in each of these intervals. So at f of 2, we had a plus 7. That tells me that we're positive in this first interval. Now at 0, for a test point for the middle interval, I got a minus 5, and that tells me that I'm negative in this middle section. And then on the right, because we use 6, I know that we're positive. We got a positive 7, so we know we're positive. So our signs went plus, minus, plus. Now let's go to the next slide. Here you can actually see on the graph how we go from plus to minus to plus, and we cross the axis at the two zeros that we found, minus 1 and 5. And so to actually write down the solution set for figuring out when our quadratic is greater than 0, we want to collect just where we were positive. So that was from negative infinity to negative 1, union 5, to infinity. That was the area where we were positive on our number line and in our graph. Now notice I use parentheses for the minus 1 and the 5. That's because we're not including those values. There's no or equals to in our inequality. So we're going to use parentheses and not square brackets. In general, the inequality for polynomial inequalities determines if we're going to include the endpoints or not. So if you have an or equals to, use a square bracket. If you do not, then just use a parenthesis. Now, in order to summarize this, so you really get this memorized for the test next week, here are your steps. What we're going to do first is move all of our terms to one side to make sure that we have 0 on one side and terms on the other. Then we're going to solve the related equation where we just set the polynomial equal to 0. We're going to use those zeros to then divide up the number line, and we're going to find out the sign on each of those intervals, just like we just did with the last example. And then we're going to actually figure out what of those intervals satisfy the inequality. So we're looking for positives or negatives, and then write down the solution. So let's do another example together. Here we have x cubed plus 13x squared minus 169x less than or equal to 2197. So let's start off by doing that first step and subtracting 2197. Whoops, 169x, 2197. We're going to subtract to the left-hand side. So now we're less than or equal to 0. Now we're going to factor out an x squared out of the first two terms. The reason my head is going there is just because notice it's an x cubed polynomial, and we're asked to factor it. So let's see if factoring by grouping works. It typically works if we give you a cubic here. So factoring by grouping starts by factoring out the x squared. I'm left with x plus 13. And then the other two didn't change. And this is, of course, equal to 0 now in this step. Now, leaving the first half alone, let's factor out a minus 169. Then I'm left with, if we look at 2197 divided by 169, we get 13. So this is again x plus 13, which is exactly what we're looking for, because then we get x plus 13 and x squared minus 169. And then that square minus the square can be factored one more time, and we get x plus 13, x minus 13 out of the x squared minus 169. And of course, then we have repeated x plus 13s. So that's squared, x minus 13. So with all of that work, we have factored our cubic. And so we know we have x equals minus 13 as a 0 and x equals positive 13 as a 0. Let's see how that looks on a number line. I'll have negative 13 marked and 13 marked. Now we plug in some test points. And we have, let's say, minus 14, 0, and 14. And we write down those test points for our function. Let's say f of minus 14, f of 0, and f of 14. And I don't have those right in front of me, but I can tell you that they are minus and then plus, or sorry, minus and then plus. Plug those into your calculator though. You plug them into the actual function here and see what values you get. So we're going to have minus plus on our number line. And so therefore, if we want to know the solution set, we're looking for when we are less than or equal to 0. Notice from over here, less than or equal to 0. And so we want to be looking at our negatives. That tells me we want to go from negative infinity all the way up to 13. We use square brackets since we have an or equals to, and we use parentheses on the other side. And that's it for this solution set. And now for our next example. Again, we want to move all of the terms on the right-hand side to the left-hand side. So starting off, we're going to subtract x from both sides. We get x squared plus 2x minus 21 greater than negative 6. Then we add 6 to both sides, and we get x squared plus 2x minus 15 is greater than 0. So now we're going to set this equation equal to 0 and solve. Of course, we got to factor first. So here we get x and x. And we think about what multiplies to minus 15 and adds to 2. And that, of course, is a plus 5 and a minus 3. So then we take x plus 5, set it equal to 0, x minus 3, and set it equal to 0. With the first one, we get x equals minus 5. And the second one, we get x equals 3. And so those are what go on our number line, negative 5 and 3. And we have our test points. And we see what the sign is of our function at those test points. And it's going to help us figure out how to answer this question and know for what x values were greater than 0. So some good choices of test points here are negative 6, 0, and 4. And if we look at f of negative 6, we're looking at negative 6 squared plus 2 times negative 6 minus 15. And that, of course, is 36 minus 12 minus 15. And 36 minus 12 is 24, minus 15 is 9. Then we're looking at f of 0. That, of course, is 0 squared plus 2 times 0, minus 15. And that is minus 15. And then f of 4 squared plus 2 times 4, minus 15. And that, of course, is 16 plus 8 is 24, minus 15 is another 9. So basically, we're getting plus, minus, plus here. So if I want to know where this function is greater than 0, because we're really looking at this function in here, where it's greater than 0, I want to look at negative infinity to 6, union 3, not 6, negative 5. Union 3, picking up at our next 0, all the way up to infinity. So reading along, make sure you pick up the 0 itself, and then thinking about where are we actually positive. And so we're positive from negative infinity up to the 0, negative 5, and again from 3 to positive infinity. I did not include the endpoints here because we do not have an or equals to. And that is our solution set. Now moving on to rational inequalities. I think rational inequality is something that can be written in the form p of x over q of x, which is greater than some number. And of course, again, the greater than inequality could be swapped out for the less than inequality or any of the other two. We're going to assume here that p of x and q of x are polynomials as well. And our critical values that we're going to talk about a lot here are the zeros of p of x and the zeros of q of x. Basically, our critical values are anywhere where the signs can change, and so we want to be able to pick them up from the numerator and the denominator, and that can determine what happens and where we might cross the axis. So to solve a rational inequality, we're going to do a lot of the same steps, but this time we are going to have a few extra things to test for. Starting off, we're going to move all of our terms to one side so that we have a 0 on the other side of the inequality. Then we're going to change the inequality symbol to an equals sign and solve that a related equation. Typically, that's going to be setting the numerator equal to 0 if there's no plus or minus a number there. Then we're going to find where our function is not defined. So that'll often involve setting the denominator equal to 0. And those steps 2 and 3 are what I'm calling my critical values. Then we're going to use the critical values and do the same test on our intervals on our number line and pick up which intervals actually answer the question. Now for an example, we want to start off by subtracting 1 from the right-hand side to move it to the left-hand side. Then we're looking at x plus 1 over 2x minus 4 minus 1 is less than or equal to 0. Now, we need to be able to look at this as a fraction ideally, or simplify this. We can't just set our numerator and our denominator equal to 0 here because of the -1. So instead, we're going to multiply this whole thing by 2x minus 4. And before we do that, let's actually write down the equals to 0 case. Minus 4. And so we might actually be able to get rid of our numerator and denominator here with this example. Because what happens when we multiply this by 2x minus 4, I end up getting 2x minus 4 times x plus 1 over 2x minus 4 minus, and then 1 times 2x minus 4. And all of this equals 0. And yes, I'd multiply the right-hand side by 2x minus 4 as well, but it makes no impact since it's just being multiplied by 0. But what happens then is that those two cancel, and I'm left with x plus 1 minus 2x plus 4. And that's actually now something really simple and easy to solve. So we're looking at here x plus 1 minus 2x plus 4. And so that's minus x plus 5 equals 0, which of course then x equals 5. So essentially, x equals 5 is when our function equals 0. That is a 0 of our function. We also want to look at when our denominator equals 0, or when the function is undefined. So that's looking at, for the undefined case, when 2x minus 4 itself equals 0. And here I quickly get x equals 2. So that's another thing that goes onto our number line. Let's go ahead and draw the number line. And here I would be looking at 2 and 5. Then we want to pick up our test points and figure out what the signs are for our function at those 3 different intervals. So if I pick something like 0, something like 3, and something like 6 as our test points, if I look at f of 0, we'll see that it's negative. If I look at f of 3, we'll see that it's positive. And f of 6, we'll see that it's negative. And so since we're looking for a less than or equal to, we're looking for where it's negative. So the solution, as I bring it back up to the top, is negative infinity to 2 union 5 to infinity. Now notice how I use square brackets at 5, because 5 we actually want to include. That came from our 0, and because we have an or equals to, we want to include that one. Now 2 is not in the domain, so we don't want to include that one in our solution set, regardless of the fact that we have an or equals to. So you always want to keep that in mind. You never want to include, of course, points that are not in your domain. So when writing down your solution set, you should always use parentheses for the numbers that come from the undefined work. Now for our next example, let's start off by factoring our numerator. Like so. And we have a minus 2 and a plus 1. And on the bottom we have x and x minus 1. So now with this example, let's think about, when is my numerator equal to 0? Basically that tells me when the function overall is equal to 0. So for the zeros, which is what I want to do first, I want to look at x minus 2 equals 0, x plus 1 equals 0, and I get x equals 2 and x equals negative 1. Then for my undefined work, I'm looking at when x equals 0, which of course, no algebra to do there. And with x minus 1 equals 0, we get x equals 1. So this time we have a lot of points on our number line. We have, in order, -1, 0, 1, and 2. And we want to remember that these ones are not in domain, as well as this one. It's just helpful to know where they came from. Then you want to use our signs, using test points essentially to solve for our signs. And let's use test points -2, -1/2, 1/2. We'll use 1.5 and 3. And using all these test points, looking at f of -2, we get 2/3. If we look at f of -1/2, we get -5/3. If we look at f of 1/2, we have 9. F of 1.5 is -5/3. And f of 3 is 2/3. So plugging all those into your calculator, you'll easily get the right-hand side, all those values I've just come up with. What this tells us is that I'm positive in the first interval, negative in the next one, positive in the one after that, negative again, and positive again. And so our solution set is -1 up to 0, union 1 to 2. And so we want to be careful about our brackets here, and we'll use parentheses throughout, since that gives us not including our endpoints. Notice that we have a less than sign here, not a less than or equals to, so we're not going to include our endpoints, and of course we don't include anything in the domain either. Moving on to our next example, we have x plus 6 over x minus 4 minus x minus 6 over x plus 4. Now to start, we need to take this and set it equal to 0. So x plus 6 over x minus 4 minus x minus 6 over x plus 4, and set that equal to 0. Now we would ideally like to get rid of those denominator functions. And in order to do that, we're going to multiply the left-hand side and the right-hand side by x minus 4, x plus 4. And then we fill in x plus 6 over x minus 4 minus x minus 6 over x plus 4. And this all equals 0 times x minus 4 times x plus 4. But of course, 0 times any number is just 0. Now looking at this, if I distribute these two first terms, I have x minus 4, x plus 4, x plus 6, all over x minus 4, minus, and then I have x minus 4, x plus 4, x minus 6, all over x plus 4. And this all equals 0 still. And see what happens is I can cancel the x minus 4 and the x minus 4, and I can cancel the x plus 4 and the x plus 4. And so I'm left with something that has no fractions in it. So now I have x plus 4 times x plus 6 minus x minus 4, x minus 6. And all of this, ignore the scribbles, equals 0. Great, now we have a couple of maybe quadratics to look at equal to 0. So let's go ahead and factor this, or FOIL this. So we're looking at x squared plus 4x plus 6x plus 24 minus x squared minus 4x minus 6x plus 24. And all of this equals 0 still. And now I have x squared minus x squared, so those are gone. And I have a plus 4x and a minus 6x. I need to be a little more careful though. I have a plus 4x minus a negative 4x. That gives me 8x. Now I have a 6x minus a negative 6x. That gives me 12x. And then I have 24 minus 24, which goes away. So this equals 0. So this gives me 20x equals 0. And as soon as I divide both sides by 20, I get x equals 0. So all of that work was to just get us to the point of finding that x equals 0 is our only 0 here. Then, of course, we want to find our undefined points, which, of course, is at where x minus 4 equals 0 and x plus 4 equals 0. From the original function, we look at those denominators. We get x equals 4 and x equals negative 4. Oops. And so those are our 3 critical values that we want to put on a number line and see where we're actually negative. So moving on, x equals 4, x equals minus 4, x equals 0. Put this on a number line like this. And then we want to pick up some test points. And so we'll test -5. We'll test -1. We can again test 1, and we'll test +5. Just anything in those intervals will work. I'm trying to pick easy numbers here where I can. Then we plug in our calculator, and I did this ahead of time. So f of -5 is -11.11. F of -1, we get 1.33. F of 1, we get -1.33. And f of 5, we get 11.11. So that tells me I go minus, plus, minus, plus. Again, picking up that I have a -11, then a positive 1.33, then a negative 1.33, then a positive 11.11. So minus, plus, minus, plus. And if we want to know exactly where we are a minus, since we're less than or equals to 0, our solution set is -infinity to -4. -4 came from our undefined set, so we use a parenthesis. And then we pick it up again at 0 up to 4. But the 0, we actually want to use a bracket. 0 came from the 0 on our function, and we have a less than or equals to 0. So it's okay to include where our function equals 0. So it's okay to include x equals 0. And that is it. Now looking at our next example, we have an application. So we have a polynomial of n size that has d diagonals, where d is given by this function. Find the number of sides if d is somewhere between 27 and 252. We're going to break this up into 2 different problems. We're going to look at when d is greater than or equal to 27. We're going to look at when d is less than or equal to 252. I prefer to have d always written on the left. I find it easier to process things the same way each time, essentially. And when you look at this, it's an equivalent inequality to say d greater than or equal to 27. Same thing as 27 less than or equal to d. Then we can focus in on these two as 2 separate problems and look at n times n minus 3 over 2. So our d value greater than or equal to 27. And then separately, we will look at n times n minus 3 over 2 less than or equal to 252. So starting off in our first case, I'm going to multiply both sides by 2 to get rid of that divide by 2 in the bottom. And I get n times n minus 3 is greater than or equal to 27 times 2. That's 54. Now let's simplify the left-hand side. I'm looking at n squared minus 3n greater than or equal to 54, which then, of course, I can subtract my 54 to the left-hand side and look at n squared minus 3n minus 54 greater than or equal to 0. Well, that's factorable. That factors into n minus 9 and n plus 6. And so, since here with this application, we're talking about sides of a function. With this one, we get n equals 9, and with this one, we get n equals negative 6. But the negative can't work. So we're left with the n equals 9 case, and we just put the n must be greater than or equal to 9. Now on the other side, doing a very similar process, we're going to multiply by 2 on both sides, and we get n times n minus 3 is less than or equal to 504. And that, of course, then becomes n squared minus 3n, and I'm going to subtract the 504 to the left-hand side. And this actually factors because 21 times 24 makes 504, so this is n minus 24 and n plus 21 less than or equal to 0. Now, again, with this, it's the same story. We get n equals 24 out of this term, and n equals negative 21. We can't have a negative number of sides, so the minus 21 case makes no sense. So we must have n less than or equal to 24 then. And so that is our solution here. We have n greater than or equal to 9 and n less than or equal to 24. If I were to write this as one line, it'd be 9 less than or equal to n less than or equal to 24. And that is it for this problem. Now we have our final example, looking at when the absolute value of x squared minus 7 equals 7 minus x squared. What's interesting about this is when we look at the right-hand side, this is really negative, parentheses, x squared minus 7. If I factor out a negative and I write it in a normal way, we're looking at the negative case of x squared minus 7. Well, this happens when essentially our absolute value bars represent the negative case when x squared minus 7 is less than or equal to 0. So really, this equation that we're trying to solve comes down to this inequality, because again, absolute value bars just take away our negative number. So when we're trying to figure out when that absolute value bars gives us our negative case, well, we're looking at when that function is less than or equal to 0. And so to solve this one, we add 7 to both sides. We're looking at when is x squared less than or equal to 7. And then we take a square root. But the weird thing that happens with the plus or minuses here is that the minus case ends up as our lowest bound. Negative root 7 less than or equal to x less than or equal to root 7. It's similar to doing a sign flip when we divide by a negative number. Same thing applies here. The negative case that we pick up from the plus or minus on the square root shifts to the left-hand side. And so this is our solution. So as always, please reach out if you have any questions.